All right, this lesson is on the fundamental theorem of calculus. The fundamental theorem of calculus says that g of x is equal to the integral from a to x of f of t dt. We need to realize that this is some function of x. This whole thing is a function of x. It's g of x. G is a function of x, and it's equal to this whole thing that is also a function of x. Recall that when we do the integral from a to b of f of t dt, that represents the area under the curve from a to b. If we don't go all the way to b, though, if we go just part way to b, from a to x, looking at the area under the curve from a to x, assuming x is somewhere between a and b. Some people refer to this as the area so far function, because we're not all the way to b, we're just part way, we're from a to x. In this example, g of x is equal to the integral from 1 to x of t squared dt. We're asked to find g prime of x. We want to know what that equals. Well, if we integrate this, we add 1 to the t, we get 3 divided by the new power 3, and then evaluate it from 1 to x. We're going to have 1/3 x cubed plus 1/3, or, remember this is a function of x, or 1/3 x cubed plus 1. But the derivative of g should just be x squared. This is g, right? This whole thing is g. G of x is equal to this function. If I want to find the derivative of g, I need to find the derivative of this function right here. So if I find the derivative, 3 times 1/3 is 1, reduce the power down to 2, plus the derivative of that constant is 0. So the derivative of that function is x squared. Which isn't that interesting that what we're seeing here in this original thing is if I'd have just taken this x and put it where the t is, I would be right there. Well, let's look at this little rule that came up down here. The derivative, d dx, right? The derivative of the integral from a is any constant. It doesn't have to be 0, it doesn't have to be 1, it can be any constant of f of t dt is f of x. Well, it's as if this x replaces that t. It's as if that happens. Let's look at this fundamental theorem here. Fundamental theorem of calculus. There's two parts. We're going to focus on the first part today and the second part tomorrow. It's really important that we make sure that the function is continuous on the interval from a to b. So if g of x is equal to this integral from a to x, f of t dt, then the derivative of g is f of x. The derivative of g is f of x. That's what we were just looking at on the other slide. This is important, and it's probably easier to think of it this way. When we take the derivative of an antiderivative, right, there's some kind of undoing there, right? A derivative and an antiderivative, they're inverse things. They should undo each other. We just get f of x. It's as if this x replaces that t. Okay? It's as if this x replaces that t. This a here has to be any constant. 0, 1, 5, 723. It doesn't matter. It's just any constant. This second part of the fundamental theorem of calculus should look familiar. It looks just like the evaluation theorem that we've been dealing with the last couple days. So let's take this to an example. In this example, we're going to find the derivative with respect to x of the integral from 1 to x squared. Now this is a little bit trickier. It's x to the fourth, I should say, of secant t dt. That's not just plain x. That's x to the fourth. Since that's not a plain x like we saw in the previous slides, we have to deal with this using the chain rule. Okay, there's a chain to follow on the x to the fourth. If it was just an x, we plug in the x and away we go. But there's not just an x, there's an x to the fourth. And we're also going to use the first part of the fundamental theorem of calculus. FTC is kind of a shorthand we'll use for fundamental theorem of calculus. So if we want, we can think of a u substitution here. We can let u equal x to the fourth, so this whole thing becomes the derivative with respect to u from 1 to u of secant t dt times the derivative of u dx. That's the chain part, right? So the u goes in here, replaces the t, we get secant u times the derivative of x to the fourth, that's du dx, right? The derivative of this thing is 4x cubed, which comes right down to 4x cubed times secant x to the 4th. So if we look at this, I think we can see a shorter way to deal with this. Let the x to the 4th go in and replace the t, and then multiply, so the x to the 4th went in and replaced the t, and then multiply by the derivative of x to the 4th, just like we're following a chain. Right? We're doing a derivative, so it's okay to use everything we know about derivatives. Chain rule, for example, that's what we're dealing with here. And we're good to go. So here's a u-try, and try to take what we learned on the last slide and try to do this quickly. If you have to rewind the video a little bit, take a look at that previous slide, and give this a shot. So, all right, here we go. So, can you see what happened here? The r squared replaced the t. So r squared squared is r to the 4th. That makes total sense, right? But because r squared is not just a simple r, we have to multiply by the derivative of that, following the chain. The derivative of r squared is 2r, so here's that. And believe it or not, we're done right there. We can stop right there. The 4 doesn't matter. This just has to be any constant, and that doesn't change the value of what's happening over here. That's it. That's our learning target for today. I'll see you in class.